Okay, so welcome back to another video. So in today's video we have this improper integral from 0 to infinity of the cosine of the natural log of x divided by 1 plus x quantity squared dx. And before I jump into the problem, I just want to apologize for not having to upload content for the past 2 months. There's a video before this that'll come out that you can watch just to give you a little update to see what's been happening ever since then. But I'm not really going to go into detail about that. So anyway, here we have this. We have some trig function, exponential function. Well, natural log of x, natural log function rather, not exponential. Excuse me. And then we have the algebraic 1 plus x squared. So clearly you can see that this is not easily integrable, as you can tell. No matter what you do, it's really going to get you nowhere. So how are we going to tackle this exactly? Well, basically the whole idea here is we're going to convert this integral into jumping into the world of complex numbers. So we'll be doing some complex analysis, manipulating some things, use a couple definitions and some formulas that you've definitely seen from past videos. So, and then that's it. And then it'll just jump straight to the value of what we want to achieve. So with that, let's go. So I like to start off with, of course, we're going to jump into the complex system. To do this, let's recall that we know that Euler's formula is defined as the exponential function e to the power I times x, and that's equal to cosine of x plus I sine of x. So now what I can do is I can actually replace our x and put in a natural log of x. And so we see that it's e to the power I times ln of x is equal to cosine of natural log of x, and then plus I sine of ln of x. But we can see we can use our rules of natural logs. E to the natural log of x, that's the same thing as well, first I would have to move the I back to the x as the power, since that's how natural logs of functions are usually defined as. So when we have e to the natural log, that cancels out. So then rewriting this, we would have x to the power I, and then that's equal to, well, now we see that the real part is associated with the cosine of natural log of x, and the imaginary part is associated with the sine of ln of x. So really, in the numerator we have from above, we have a cosine ln of x. So what this entails is that we're actually going to have to take the real part of the integral. So I'll just rewrite this, and we'll write it like this. So I'll just rewrite the same integral. So it's from 0 to infinity of our given. So, and then 1 plus x and then squared dx. Rewrite this. I'll take the real part, and then this time same bounds, but this time replace the cosine of natural log of x with in the world of complex analysis. We're going to take this as x to the power I, and then 1 divided by 1 plus x quantity squared dx. So now let's actually recall, we're going to be using a little function. We've used this a couple of times. This is the beta function, and this beta function will take in 2 variables, capital B of s of t. Well, I'm just writing down the definition of this, and that definition of the integral of the beta function is defined as this integral, the integral from 0 to infinity of x to the power s minus 1, and then that's being divided by 1 plus x to the power s plus t dx. Okay, so we'll just use this and then rewrite some terms from what we see from over here. So then we'll have to find what our s and t is equal to. So judging from over here, what I'll do is I'll just rewrite that same integral. So let's see, 0, infinity, x to the power I, and then divide by 1 plus x quantity squared dx. So let me write what our s and t is equal to in black. So we'll just do a little comparison. So we see that the s minus 1, so I'll set that equal to I. This just corresponds with each. So s minus 1, we set that equal to I. So doing some algebra, we see that s has to equal I plus 1. And so the next part we have is s plus t. We set that equal to 0, or set that equal to 2. So then that means we'll plug back what s is equal to, so it's I plus 1 and then plus t equals 2. So therefore, if we do the math, then we get that t is equal to 1 minus I. Okay. So therefore, we have that this integral over here, just an arrow, this is actually equal to beta of I plus 1 and then comma 1 minus I. So that's what the beta function is in this integral representation. But also recall that another way to write the beta functions is in terms of gamma functions. So we know that here, beta of s comma t, if we write this in terms of gamma function of gamma, that's also defined as gamma of s multiplied by gamma of t, and then divide this by gamma of s plus t. And then I'm going to use a couple facts over here about what we know about the properties of gamma functions. So we know that, here, I'll write this in red, how about that? So we know that gamma functions of property. We know that gamma of s plus 1, that's equal to s multiplied by gamma of s. Another property we know is that the standard definition of a gamma function is just equal to, of s specifically, is just s minus 1 factorial. All right. And then another calculation we're going to be doing is, and I'll just write this down, is that we know that gamma of 2 is basically just equal to just 1. You'll see that you just plug 2 in here. 2 minus 1 is 1. 1 factorial is just 1. Okay. So we have that. So we know that what our s and t variables are. Now, write this as beta of, let's see, I plus 1 and then 1 minus I. Therefore, we set this equal to, in terms of gamma, this is just gamma of I plus 1 multiplied by gamma of 1 minus I. And then this is being divided by gamma of s plus t. And if we do the calculations, we see that the i's would cancel and we just have 1 plus 1, so it's just gamma of 2. Okay. And now if we rewrite things a little further, we can simplify some stuff. We know that gamma of 2 is equal to 1, so we're just left to focus on the numerator. And we know that gamma of s plus 1 is equal to s times gamma s. We just let s equals I, for example, in this case. So we can rewrite that as I times gamma of I, and then multiplied with gamma 1 minus I. And now here's another thing that we're going to be doing. Another definition, another formula and theorem that you've definitely seen this before. I actually did I did cover this in one video a long time ago, is actually Euler's reflection formula. And then this formula is defined as follows. So this is just gamma of s for some variable s multiplied with gamma of 1 minus s is just equal to pi divided by sine of pi times s. Pi of s is just the input. Okay, so I mentioned I did a cover on this video a long time ago. So if you want to check out the whole the full derivation of this formula, you can click that. I'll provide that video link in the description below for you guys to view. We're just using this formula, and so let's see if going from over here we can actually just substitute some terms back in. So in this case we have, in this case, s equals I for here. So then now I'll worry about this I in front of the gammas later. So let's just write this as gamma I and then gamma I, or 1 minus I. So far that's just equal to sine of pi times I. The next thing is that, okay, of course I'll just multiply to I, but let's reiterate what I just wrote, what we started with. So far from this integral, so we have the improper integral of x to the power I and then divided by 1 plus x squared dx. So far we showed that that's just equal to I times here, so this is I times pi divided by sine of pi I. Okay, and now the next thing we want to do is I want to use the following relationship to find. So we know that, and the proof is actually really simple. I'll show this too. We're going to use the relationship that sine of I times x is equal to I times the hyperbolic sine of x. Let me fix that. And the proof is really simple here. So you see that if I start off with sine of ix, using the definitions with the exponential functions, we know that sine of x is defined as e to the power I times x, and then subtract that with e to the power negative ix. So if I put I times x into here, so really we're going to be left with e to the power I square x, and then minus e to the negative I square x, and then and of course divided by 2i. So we have this I squared, we know that that's just equal to -1, so therefore we have that this is e to the negative x, and then over here minus e to the positive x, and then divided by 2i. And so what I'll do now is that I'll just multiply and divide an I, so we're just manipulating the equation with the number 1 and then doing some manipulations. So if I multiply I into here, so that'll be a -2, and then over here it's just I, and let's see, e, and then negative x, and minus e, and then x. And then what I can do is, of course, I can actually just rearrange the terms, and but there's a negative, so what I can do is I can actually factor out a negative and do some commutativity with the addition. So it's we would have negative I, and then this will be e to the x, and then subtract that with e to the negative x, and then all this divided by -2. Really, I should have put the parentheses with corresponding with the -2. Well, we know that by definition of the hyperbolic sine function of x in terms of complex exponential functions is actually exactly this. So replace the e to the x minus e to the negative x, and then divide by 2. And of course the negatives cancel out, so then we have just e to the, or excuse me, I times the hyperbolic sine of x. So that's the proof done for here. So of course, as I mentioned, I'm going to be using this relationship to rewrite the denominator from here. So then now we have this same thing, I times pi, and then this will be I times sine of, this will be I times the hyperbolic sine of pi. Okay, and then we see that of course the i's cancel out, so we're just left with pi, and then divided by the hyperbolic sine of pi. Okay, and actually we're just about done. So we showed that this this improper integral here is equal to pi divided by hyperbolic sine of pi. So the last step really is that we have to take the real part of this integral, but pi divided by sine of h, or hyperbolic sine of pi, that's actually a real value, and it's not multiplied with some imaginary unit. So really, that means the real of, rewrite this again, the integral x to the power I, and then 1 plus x squared, or 1 plus x quantity square, is basically we take the real of pi hyperbolic sine of h, or pi, and so that's just equal to just pi divided by hyperbolic sine of h, since it's a real value. And so in conclusion, we can say that the integral that we are given, the integral from 0 to infinity of cosine of ln of x divided by 1 plus x quantity squared dx, is simply just pi divided by hyperbolic sine of pi, like so. Alright then, and there we have it. Yeah, now it's pretty cool if you ask me.